So, this is a very elegant way using hollow thin tube theory that we can calculate your cracking torsion and your twist per unit length for an applied torque. Now, there is one more theory that was proposed in 1970s. So, it is called skew bending theory. So, what we are doing is, for any cross section that is subjected to, let us say if you apply your right hand rule, which is subjected to bending and torsion. Torsion is a moment about longitudinal axis, and let us say primary bending moment we are talking. So, this will be like this. So, there will be a resultant bending moment that is acting like this at an angle, right. So, when you have a combined flexure and torsion, so that whatever that bending and twisting moment that is acting in the cross section can be converted into resultant moment vector. Now, based on the magnitudes of your twisting moment and bending moment that is acting in the cross sections, you can have three different failure modes that are possible. The first one is a modified bending failure. So, that means my bending moment is much higher than, you have some torsion, but the torsion is not that significant. So, the behavior is still dominated by bending. So, that is the reason we call that as modified bending failure. So, if this you see here, this if mu is very high compared to of less torsion, then you will find that your bending moment will dominate, your resultant vector will get close to that of your moment vector, right. So, that means your bending action will dominate the behavior. So, let us assume a simply supported case which is creating a sagging moment. So, you are going to have compression on the top surface and tension in the bottom. So, but instead of having a section perpendicular, now I will have a skewed failure surface, but still my compression is still going to be at the top. Okay. So, that is the reason we are saying that as a modified bending failure. So, this will happen when you have large bending and let us say small torsion, right. Okay. Then mode 3 is a lateral bending failure mode. So, when you have very slender beams, okay, when you have very slender beams, then you can have this kind of a bending failure. That means your compression is going to, here also again you will have a skewed failure surface like this, but however your compression is going to be on the side. Okay. So, that is called lateral bending failure mode. Okay. So, you have here you can say both mu and tu are reasonably high numbers, but however the slenderness of the section also will come into picture. Okay. Now, the next, the common mode is a negative bending failure mode. So, what is the meaning of negative bending failure mode? Now, here in this case can be torsion is going to be much higher than let us say bending. So, what torsion does is it creates tension on the entire all the four sides of the cross section, and bending, you know, it is going to create, depending upon whether it is sagging or hogging, it is going to create predominant tension in either top or bottom depending upon its sign. But torsion, if you see, is going to create tension on all the four sides. So, if your torsion is going to be very significant compared to that of bending moment, then what will it do? The bending, you know, for a section that is subjected like this, you know, it is. So, what kind of strain distribution that we say? Let us say you are going to have like this, right. So, we have studied, let us say this is compression, this is tension. Now, for a section that is subjected to torsion, I am going to have, maybe I will write it here. So, I am going to have maybe everywhere that you have going to have tension. Let us say this is T1 and T2. You are going to have all across the depth you will have tension. So, what can happen is, now let us say this is due to torsion, right. Now, I am creating tension here, and due to bending, this is bending, I am creating compression here. If this T1 is greater than C that is coming from bending, then what will happen? The net effect will be tension at the top as well, right. So, that is what we are saying here. if your bending moment is, or if your twisting moment is significantly higher, that can create tension in such a way that it can compensate the compression that is coming from bending, and you can put your bars at the top in tension. Okay. So, that is what we are seeing. Okay. So, it is as good as having a bending moment in the opposite direction. So, that is why we call this as a negative bending failure mode. So, we have to design for that. If your torsion is going to be very high, you can have a situation that the compression that is created from bending can be nullified, and the bars in the compression side can get into tension, right. So, then we need to design for that by providing some additional reinforcement. So, that we need to account for that. So, that is what this mode 2, which is a negative bending failure mode. Okay. Now, skew bending theory, I think it was the several expressions have been derived for all the modes. So, let us look at this one particular mode, which is called as modified bending failure mode. Okay. So, they take this kind of a skewed failure surface for the same cross section. This is the surface that it is creating that failure. Now, you see here, with respect to this beam axis, they are saying that this particular the failure surface is going to create an angle theta 1. Okay. It is an assumption, and you will have multiple things. You will have AS, you will have stirrups, AW, right. This is longitudinal bar, right, and this is stirrups. So, depending upon the locations of the stirrups. So, now stirrups will have both horizontal legs and vertical legs. Okay. So, if you take, so you have to look at all the internal forces. So, that is why you have this Fs, which is the tension force that is coming from longitudinal bar, and Fwh is basically the tension force that is coming from the horizontal leg of the stirrup, and Fwv is the force, the tension force that is coming from the vertical stirrup. So, you have this plus this from torsion, right. So, you will have circulatory shear. So, that is why you have it here, and then you have compression force that is creating like this, okay, and this is your compression force. Now, we are going to make some assumptions where those locations are and all. So, this Yp is, for example, if you look at it, the location of this pre-stressing strand, for example, FPS is at a distance, we are saying that at a distance of Yt. Now, what is Yt? Yt is the location of your tension force from the centroid of your compression force. So, everything is expressed as a function of your Yt. So, with and then you see here this particular surface at this location, the distance it is going to be at a distance of b tan theta 1 from your simple trigonometric calculations. We can show that if this is b and this distance, if this is b, this is going to be b tan theta 1, right. So, with all these notations, what we do is we are going to now look at, if I take moment about this axis AA. Now, see, these are external, okay. You have twisting moment and you have bending moment, both are acting. So, these are external forces. Now, we are trying to see, I mean, these are the internal forces that are there. Now, how the resistance is going to come, we are going to invoke equilibrium and find out. Now, if I take a component for twisting moment, which is perpendicular to this inclined surface, it is going to be T sin theta 1. For bending, it is going to be m cos theta 1. Now, FPS is the force that is coming from a pre-stressing strand, and that is going to be at a distance of Yp, which is what we are calling that as beta 1 into Yt, and similarly there is going to be, okay. So, both this moment has to be resisted by the force in the pre-stressing strand multiplied by this lever arm, similarly force in the tension steel, and I am taking a component that is perpendicular to this inclined surface. That is the reason this cos theta 1 and cos theta 1 coming. These are a component that is perpendicular to this surface, right, and Yt is the lever arm. Similarly, for stirrups as well, this is the horizontal component, this is the vertical component. Now, when you do all of them should be equal to the moment created by the twisting, the component of the moment created by twisting moment and flexural moment. So, if you do that, if you do some simplifications, as I explained, FPS and FS are the longitudinal forces due to pre-stressing and reinforcement bar, and FWH and FWV are the horizontal and vertical forces in the stirrups, right. And then here you see here there will be a vertical component of the vertical stirrup. When you take moment about this AA, and when you further this entire thing, when you divide it by the component, that is going to be very small. So, you can ignore that. So, this component, basically this component becomes small, or I should say negligible, right. Okay. So, this is basically the tension force multiplied by the lever arm from pre-stressing steel and the non-pre-stressed steel, that is, we call that as M0. That is a major resistance component coming from bending. So, this reinforcement contribution is taken as M0, just a nomenclature, whatever that moment contribution coming from this pre-stressing strand and steel is taken as M0, right. So, if you do that, and then if you look at FWH as well, now YT can be expressed as, if you see, this is a again FWH is that FIW times x1 into B theta 1 divided by S into B plus 2BH. So, this is again we are looking at only the force that is coming from horizontal stirrup, okay. The horizontal stirrup, whatever that component, that we are trying to simplify this, and you will find that that is going to be equal to x1 times tan theta 1 divided by S into 1 plus 2 alpha. Now, what is alpha? Alpha, I am taking that as a ratio, which is basically, we say if we take B out from here, it is going to be H by B. So, I am putting alpha equal to H by B. So, this bottom will become B, if I take it out, it is going to be 1 plus 2 into H by B. So, I am writing H by B as an alpha, and B will get cancelled from numerator and denominator. So, some simplifications that we are doing, right. So, that is all. So, finally, what we can do, so we can, so what we are trying to get out of this is, somehow can we convert the torsion into an equivalent bending moment. So, that is what we are trying to see. So, if you simplify that again, if I take what is psi now, psi is the ratio of T by M, okay. So, if I take T out here, you can see that tan theta 1 plus 1 by psi. So, if you put again T by M psi, T will get cancelled, so and then you will have M. So, you can simplify, I can get this equation 13. Now, with further simplifications, I am defining this, that what the component of this horizontal stirrup is some R, and I put this into this equation, then you will find that T can be again further simplified in this form, okay. So, these are all given in this paper. I am just reiterating it to show how our IS code is actually converting the torsion into an equivalent bending moment. So, that is why we need to look at what are the origin of these equations. So, for more information, actually you can look at the research paper as well. So, if you try to express this T in terms of M0 and this psi parameters, so you see that everything can be expressed in terms of this theta 1 like this. Now, the value of theta 1 can be minimized, basically it minimizes a T and defines actually the failure surface, okay. So, if I to find out what theta 1 that it will create to define the failure surface, basically we are taking the first derivative and equating it to 0. Then if you do that, it can be expressed in the form of, let us say the tan theta 1 is taken as x. I want to express this in a simple quadratic form. So, you can say that as m0 into 1 plus r x square by 1 plus 2 alpha divided by x plus 1 by psi. So, if I do this equate to 0, then we get this particular quadratic equation. So, basically that is what it is. So, r x square plus 2 r x by psi is equal to 1 plus 2 alpha, and on solving the quadratic equation, and if you put x is equal to tan theta 1 and you can find an expression for tan theta 1 in this form, equation 17. Now, this 17 whatever that we found, that if you put it back into this equation 15, then you can find an expressions for your T1 that is going to create this resultant, the vector that we talked about, that is going to define this inclined failure surface, which is the modified bending failure surface. So, this is the way that we have we can form this. Now, why do we do this? Again, if I take some common values for alpha and I can find out an expression for any given T and M, how torsion can be converted into an equivalent bending moment. So, that is what the whole idea is. So, that is how we get this. That is why this becomes an important. So, if I assume some psi value, which is the ratio of your torsion to bending moment, and some alpha value, let us say which is equal to 0.4 or so, then I can put everything back and I can convert torsion into an equivalent bending moment. So, that is what our goal from this particular equation is. Okay. Now, we can do the same thing for that negative bending failure also. Again, you define that failure surface from the horizontal angle as theta 3 like this, and then you take all the components. Now, you are going to take moment about this CC line. So, if you take the moment about the axis CC, and again you will have a component from torsion, a component from bending moment, and it is a negative bending failure. That is the reason the sign here is negative, and because the component will be now in the opposite direction. So, with further simplifications, now here you see here there is a bottom steel that it is coming. So, that is the reason that we are saying that it is going to be F prime S into YC now, right. So, this is the force that is going to be there. So, with further simplifications, we can again for converting for this particular failure mode, negative bending failure mode, again how do we convert the torsion into an equivalent bending moment can be coming from this particular equation after some simplifications. Again, I can assume some typical alpha values and psi values, and then I can find an expressions for my MT, right. So, that is what the whole idea is, right. So, these are all some factors that are there. Now, R3 is basically M0 for the third failure mode to M0 for the first failure mode. So, that is your R3 factor, and you can plug all these values to get your torsional moment in terms of your M0. Okay. So, these are all some of the parameters that you can look at it at a later. Now, same thing we can do it for lateral bending mode as well. So, again if you take the moment about the axis BB, then you will have this kind of, this is from again torsional moment and the shear that it is acting here, and then if you simplify that further, then you will find that you can again the torsion to shear ratio here is defined as E. This comes from your actually from your structural analysis. Right. So, again further we can simplify that and find an expressions for your torsion in terms of M0 and alpha parameters and psi parameters like this. Okay. Okay. Now, after cracking, so this is from skew bending theory. Now, why the skew bending theory and all these equations we need to at least have an idea is that is what it is there in your IS 1343. Your design is based on this skew bending theory.